Hi, so in this video I want to give you a fairly quick demonstration of the new Decode Orc. And Decode Orc is the new decoding orchestrator that is to replace ld-decode-tools. So let's start off with a quick demonstration just to show kind of the style of it and what it can do briefly. Let's just load up the GUI. So let's say we want to take 10 seconds of a TBC, which we've already decoded, and we want to output it as an MP4 file. We want to have audio and we want to have subtitles. How would we do that? So first of all, we need to start a new project. We'll start a new NTSC project. Call it test 3. Now we will add a source. So source is basically defining the input TBC to what we're doing. Let's take that. Okay. We'll take this, which is about 10,000 frames of Disney's Bambi. So immediately we get a frame preview window. If we've got our source selected, we can actually then go into it and see that there is 10,000 frames in here. So the first thing we want to do is knock that down a little bit. We want to take a field map, connect that. And we want to take, let's see, just do a quick field mapping range. We want to take between, let's say, 5 seconds in and 15 seconds in. That will give us a 10-second sample. Let's just run that. The tool will work out what that means in terms of fields. We apply that. And now in the field map, we should have, and there we go, 299 frames, which is approximately 10 seconds in NTSC land. So once we've got that, we probably want to then do a dropout correction on it, as that's kind of a normal requirement. And then we want to sync that to an FFmpeg video sync. And we said that we wanted H.264. Let's just select that as an output format, and we want to give it a place to be. So we will call that Bambi 1, for example. And we want audio, and we want subtitles. Okay, let's tidy this up quickly. A quick arrangement and save our project. Now, well, we can quickly look if we want to see what it looks like after it's been through the video sync. But basically we just need to trigger this stage, and you can see here it's outputting 300 frames. Once that's finished, we should be able to then go into our file system, go to the video out, and and then we have 10 seconds. Turn on the subtitles, we should be able to see those too.
Hi, Bambi. Watch what I can do.
And that's it. We've basically gone from a TBC to an MPEG-4 with analog audio and subtitles in just a couple of steps. So now you've seen Orc Decode working, it's probably a good idea to sort of talk a little bit about what this is and what it means to be an orchestrator as opposed to the ld-decode tool chain that we had before. So Decode Orc basically takes a new approach compared to the legacy ld-decode tools. The ld-decode tools consisted of loosely coupled utilities that passed video field data and metadata between individual executables. Processing order was implicit rather than enforced, and the metadata content varied depending on which tools had been run on the video and the metadata. But Decode Orc is an orchestrator that manages the processing of video data using a DAG, which is a directed acyclic graph. A DAG is basically a set of linked nodes with a strictly non-repeating execution path, so it can't contain any cycles. So within the chain, the video fields are the smallest atomic navigatable units, so really the smallest individual pieces of data that are handled by the system. So these units are represented using what's called a VFR, a video field representation. And the VFRs are what's passed between the different stages as they move through the DAG. So here you can see a DAG, and you can see it has 4 stages in it, and there are basically 3 different types of stages that are supported at the moment. You have source stages. These are the stages that ingress or ingest data from the outside world. So this could be coming from, this case, in ld-decode, it could be VHS decode, it could be a number of other tools. You can add as many of these source types as you like. And the source is responsible for taking the whatever the video format is, or the field format, whatever the metadata format is, and converting that into the VFR. Then you have transform stages. These are the stages that take the VFR and perform operations on it, either on the actual video data itself, or on the data around the video, or on both. So an example of this is what you've just seen, where I used field mapping, and field mapping took the input VFR and then restricted the range of it so that we got that 10 seconds that we were looking for. And another example of a transformation is the dropout correction stage, which is performing dropout correction. And again, we can look at the parameters of that. Then finally, once you've taken the source, you've done the transformation on the source, what you then want to do is sync. So it takes the VFR and it syncs it to whatever external format you want. And in this case, we used an FFmpeg video sync, but we could have just as easily decided to sync it back to ld-decode. So this type of sync will produce a TBC and a SQLite metadata file as well. So you can use Decode Orc, and then you can take the output from it and you can drop that back into the original tools or an external tool that was dependent on the original format. You can also see something else here, that it's possible to fan out from stages as well. So the dropout correction is producing one VFR stream, but I can actually fan that out to multiple syncs or multiple transforms or multiple anythings if I want. So if I wanted to have, say, a separate file for the subtitles, as an example, what I can do is I can remove this sync stage here. I can add a new sync. Let's add a closed caption sync here. I can fan out from the dropout. So I'm using exactly the same data. Obviously, I need to tell it where I want to store that. Let's just do it in plain text. And we'll call it, let's see, video out. Subs.txt, for example. Save. Okay. And then if I was to trigger that stage, then that would trigger the output of the subtitle file, which we should be able to find in here. And there we see exactly what was in there. So now you've seen it working with a simple file, let's do something a little bit more complicated, just to show how these transform stages work together to do various operations. So if we were to take a new project, let's take a PAL project this time. We'll call it PAL test. There we go. We'll add a PAL source. Let's take British garden birds. This is a nice old PDO disk from the UK, so it's always absolutely full of dropouts and all sorts of errors. So this should just be a few fields from it. Yeah, we've got 31 frames in here with a nice shot of a pigeon. So if we look at this and we look at dropouts, for example, we should be able to see in here, there we go, various dropouts happening in the image. So what we want to do, obviously, is usually we just want to do a dropout correction on these. And we obviously then want to sync this to our target video. So let's just set this up quickly so that we've got a complete project. Let's configure the export, and we'll use 264 again. Just audio this time, since there's no closed captions on this disk. Let's give it a sensible output file name. Just call that BGB1, British Garden Birds 1. Okay. So now we have a nice project, which if we run and trigger, we will end up with a MPEG-4 file that we should be able to view already. Let's have a quick look at that. British Garden Birds, there it is.
Black, white, blue. It's black, white, blue. It's black, white, blue. It's black, white,
Okay.
blue.
But generally with these types of files, you can see, for example, here, there is a dropout that's been missed by ld-decode, so it's not been marked. So one of the things that you can do in here is we can bring in a new type of transform called a dropout map. And what we can do with this is we can insert the dropout map between the source and the dropout correction. So the dropout map allows us to look at the dropouts contained within the file. Zoom in on this. So here's the dropout that we saw. And what I can do is I can add a new dropout hint. Oh, missed it slightly. There we go. It's on there. We can even scroll around here and look for other ones that we missed. I'll add a few dropouts in here as well. Do for now. Look at the next field. There's one there that we can correct. We can even look at fields that have dropouts already, and well, there's no real point in doing this, but we can select those and we can even override those as removals as well if we want to. So we can tell the dropout corrector to ignore particular dropouts if we want to. Once we've done that, we can say OK, and you'll now see that the dropout map in its parameters has content that's been generated by our nice dialog. And what that means is if we look now at frame 0 where there was no dropout before, you can see there's now a highlighted dropout in the different places where we added those dropout correction hints. And that means if we go to the dropout correction now, we'll be able to see that those missing dropouts should have been picked up by the corrector, yes, and now they're gone completely. So what this means is that you can actually manually control something like a transform node, so you can add into it different dropouts. So this also brings us to another important thing, which is observers. So actually within the DAG you have stages, and stages have observers, and sources have hints. So things like dropouts, you can't really detect them by looking at the video field representation itself, because the dropout information kind of comes mostly from the pre-demod stage in ld-decode, where it's looking for dropouts in the inbound RF data. So those things that we can't recreate in the chain, those are called hints, because they are hints that are provided by the tool. So here you can actually see the video parameters, for example, which are another example of hints. So the inbound IRE levels, these are all determined by ld-decode. So they're just passed in the metadata and we accept them as hints. And of course, you've just seen that it's possible to add additional data into the VFR that overrides or augments the hints that are coming in. But we also have this thing called observers. So sitting on the output of every single stage is a series of observers. And the most obvious one would be the VBI decoder, for example. So the VBI decoder is sitting on the output of this. It's looking at the VFR, and for every single point in this, every single stage on the output, there is another one of these decoders, or one of these observers, sorry, that will look at this data. So what this means in practical terms is that as the DAG executes, you can see the effect on the VFR of the things that have been executed in the DAG. So here you could, for example, look at the source. If we were to bring up a dropout analysis and look at dropouts in the first frame here, you'll see that there were no dropouts whatsoever. If we look at the dropouts at the dropout map stage instead and bring that up and do a dropout analysis, we'll see that the observers have now seen 71 pixel dots or picture dots of dropout data. So the dropout view here is not the same as the dropout view here. And similarly, if we look at the dropout corrector, which will take out all the dropouts, we shouldn't see any dropouts at all at that stage. And this is not just true of dropouts, it's also true of things like if you look at the burst level analysis or the SNR analysis, As the DAG executes and does things to the signal, you could be doing stacking, for example, that will improve things. The observers at the output of every single stage will be picking up on this and giving you a view anywhere in the execution chain to tell you what's going on and what's happening to the various data. So if, for example, the SNR gets better, you'll see that. If correction causes VBI data to be improved, you'll see the improved VBI data as well. So generally you can see the observers and hints. Well, the observers here are per field or frame that you're looking at, so the quality metrics, for example. And also in here you have in the stage tools ones that will analyze all of the fields that are available. So these can take a little while to generate if you've got a big file, but it's across the entire source at that point. Okay, so let's take another example of what you can do to sort of show the power of these transform stages. And it's worth mentioning that the transform stages are deliberately quite generic in their functions. So we're going to do a little bit of playing around with field mapping here, but field mapping is pretty much anything that requires you to move fields around. It could be, I want 10 seconds of this source. It could be, I want to flip the order of the fields around. It could even be doing things like what we used to call disk mapping, where you analyze the source and you decide exactly how to map every single individual field in different orders to pull it back and pad it. So let's have a quick look at how that works. So let's start with a project. Let's take a NTSC project again. We'll call it map1. Okay, we'll add a NTSC source. And again, we'll use the Bambi that we used before. Here we go. Okay, so now we have the source loaded. So the first thing we want to do is we want to take 10-15 seconds of this particular source so that we're not playing around with too much detail. So let's take a first map, and this first field map is going to be just a quick cut. So let's just rename the stage. We'll call this one cut so that we know what it's doing. And what we want to do in here, we're going to use one of these stage tools, which is kind of a helper. So the parameters are here, which are not very useful really if you're a person, but what's produced by all of these different tools can be hand edited. So if you want to do something really particular to the field ranges, you can go in here and you can change it yourself. But usually what you would do is, in this case, we would use the field mapping range tool. And we want to take from, let's say, 15 seconds in to 25 seconds so that we a 10-second sample. Actually, let's make that 15 seconds. Okay, so we run the analysis. The tool will go away. It will look at the input source and work out what fields, basically, what we're asking for represents. We apply that to the node. And you can see what actually happens here is in the field map parameter, it's automatically filled that in. This is quite simple. It's just a simple range. So it says fills 900 to 1798 are the 15 seconds we're asking for. And you can, of course, click on that, and then you can see that in the frame preview that we're here, we've got 15 seconds. In fact, we could use the VBI decoder to look at that. This is 15. And then all the way at the end, we should see, 29.28. So the next one would be 30. So that's correct. Oops. Let's not kill that just yet. Okay. So now what we want to do is we want to do a different type of field mapping. If we want to demonstrate how the field mapping tools can reassemble a broken source, so with disk mapping that was in the old tools, for example, one of the things that we can do is we can make it a bit easier on ourselves when we come to test these things. So we put a field mapper in, and what we want to do is we want to use the field mapper to break the inbound source, which sounds a bit counterintuitive, but it's quite useful for testing. So here we actually have a field corruption generator. And the field corruption generator can simulate various different types of damage to a disk. So we're going to do mixed heavy damage. So if we run that, it will use a random seed, and you can see here it's produced quite a complicated set of output. And this is 0 to 15, then 26 to 40, then frame 51, then 62 to 65. It really messed it up basically. So if we were to apply this and look at the output from it, what we would see here would not be a contiguous range of frames. It's kind of a bit difficult to show. So what we're going to do is we're going to take this as a field map. We're going to add in a sync, and we're just going to drop this out to an MPEG-4 so that we can actually visualize what it looks like. So let's just give this a name so we know what the field map is doing. Corrupt, we'll call it. And again, just like before, we have to go in here and we have to configure our output format. We'll do a H264 again. Let's give it a name. We'll do out and we'll call it mapping just so we can find it. We'll include the audio and we'll include the closed captions. Okay. So we okay this. Let's clean this up. Range it. We'll save it just to be sure, and then we will trigger this. So let's have a look at what that's produced. And you can see here that originally when we cut, we had 448 frames, but the field map has dropped a whole bunch of stuff. So we've only got 293. So there should be some pretty heavy jumps going on in the output data. Let's have a look at it. Okay. So if we were to take that as being a input, we want to now do a field map that undoes the damage. So just like a disk mapper used to do in the old toolchain. And again, this is exactly the same type of transform. It's a field mapping action that we want to do. So we want to take the field map and we want to insert that into the chain again. And we'll just arrange that. We can give this a name and we'll call it correct. Oops. And then what we're going to do is we're going to do a field mapping analysis, which is basically what the old LD disk mapper used to do. So you can see here it has the same parameters. We run the analysis, and what it does is it looks at the gaps, it looks at the repeating fields, it tries to remove them. And here you can see in the generated field mapping there's pads. So the pads are basically it adding additional frames, just blank frames, that will stretch this out and put it back to the correct timing that it used to be, within the realms of how many, the maximum and minimum frames that were available. So you can see various different statistics about what it did and how it worked, just like the original disk mapper. If we apply that, and then save this. Now what we're going to do is we're going to trigger this stage. Now what we should see here in the generated video is not just the padding working, but the VFR also contains the field audio and EFM data as well. So as it goes through correcting, even though it can't pull back the audio data that's disappeared because of the corruption, what it can do is correctly pad the data so that the audio data always matches with the video data that's being shown. So let's see that working. Here we go back to mapping again and play. What you can see here is that we've got exactly 15 seconds of video again. It might even be possible to see the subtitles. There we go. So not exactly a great video, but it does demonstrate the principle of the VFRs being going through, in fact, 3 different types of field mapping. One to cut us down to 15 seconds, one to absolutely mess it up, another to guess at correcting it, and then outputting it back to the sync and seeing again. So you can see here quite easily how, when you've got multiple sources and you start to do different types of mapping, you're able to reconstruct those sources back together again. Now, finally, what I want to show you is a multi-source map. So what we're going to do here is we're going to take multiple sources. We're going to map them so that they're all aligned. Then we're going to stack them together and we're going to produce one single output file from all the inputs. So let's have a look at how to do that. We'll take a new PAL project and we'll call it UN1 for good reason. And then what we're going to do is we're going to start adding in sources. So we're going to take these sources. So let's just browse. So we're going to need quite a few sources for this. I've already prepared this. This is 7 different disks, 6 gigs per disk of UN&U, which is a very old British training disk. Not very interesting, but I happen to have 7 copies of it. So we'll take source number 1. And you can see here it pull in the PCM as well. Okay. And just to keep track of this, we'll rename these sources. So let's just call this source 1. Okay, then we'll add a node, another source. And this is usually the point where I speed up the video so you don't have to watch me doing all of this stuff. Right, to stop this from getting too complicated, we'll stop at 5 sources. Should be enough to get the point across. So we have 5 sources, but of course one of the problems with stacking is that for stacking you need to have exactly the same field ranges coming in, and those field ranges have to be aligned so they all start and stop at the same point. So to be able to do this, the first thing that we need to be able to do is we need to add in field maps. So let's add in the field maps. And obviously we need 1 map per source. There we go, link them together. Right, now we've got them neatly linked together, we have to go in and we have to use the field mapping analysis, which will of course look for any repetitions, it will look for any gaps, it will look for missing fields and all those sorts of things that can be problematic, and I don't think we're going to see very much in here. No, this just took 2 to 9999. We apply that to the node. It's done. And we do the second map. Again, use the tool to do the analysis. Run the analysis. And of course, if you're sure of your sources being aligned, then there's no need to do this step. You can just quite happily miss it. But it's a good idea to make sure that your maps are all equal and in place before you try to do any stacking. So let's just carry on with this. Okay, so now we have 5 sources with 5 individual field maps. So the next thing we need to do is we need to align these sources to make sure they all start at the same point. So to do that, we connect a source align stage. And you can see here, the source align stage has a little dot in the input here. What that means is it's a many, well actually in this case, many to many. So these are 1 to 1, but of course you can fan out. But this is actually 1 to many. So that means I can take multiple VFRs or many VFRs and connect them to this one particular stage. So it's designed to take multiple inputs. So once we've got all the stages connected, we can then go into source align. And then what we want to do is a source alignment analysis. which will look and it will find the first common field in all of the input sources or the input VFRs. So you can see the field ranges from 0 to 9998. This is the same. So they're all neatly lined up. But of course, if you have a bit more of a messy sample solution, or you have samples from different bits of disks that not all the disk plays, this will go all over the place, as you've probably seen with the previous ld-decode tools. So once we've got a source alignment, we apply that to the node, close that, and we can look at the parameter, of course. And again, here you can see how it's lining up the different sources. And again, like with all of the other tools and their parameters, you can go in here and override this manually if you need to. Once you've got the sources aligned, the next step is, of course, to actually stack them. So we use a stacker, which is capable, again, of taking many VFRs. But you can see here, there's a dot here, but there's no dot here. So this is many to one. So many VFRs can come in, only one VFR goes out. And of course, once it's gone through the stacker, what we then can do is we can look to see if there's any further dropouts. Anything the stacker didn't manage to catch, we want to correct. We'll add a dropout correction in there. And then we need to add at least one sync. Let's start with a FFmpeg sync as usual. So we'll select the stage tool. Let's configure this to export to H.264. Browse here. And in video out, we will generate UN1, we can call it. Okay. And we want to take the audio as well from that. So here we go. Right. So that will work fine, but we can also, of course, add more syncs if we want as well. So if you want a, an analog audio, let's say that we want a WAV file to come out of this as well, just a WAV file of the audio. And remember, the stacking here operates on the video, the EFM, and on the analog audio. So the stacker will actually stack the 5 analog audios coming through as well. So we should have a much higher quality WAV file by the time we're finished. Again, we just need to give this a name. So we'll go in here, video out, and we'll call it un1.wav. Okay. Let's trigger the video stage. This can take a little bit longer, of course, because we're now dealing with quite a lot of data. I'll just speed this up. Right, so that's complete. So let's drop the audio out as well by triggering that stage, which will be much faster. Now we can bring that up and we should be able to see the result. So let's have a look at the MPEG-4. Even with 5 discs stacked, it's not perfect quality, but that's PDO for you. And you can see that we do actually have a video from here.
New York, le siège des Nations Unies,
and the
où se
United
réuniront
Nations
les
headquarters
This
candidats
is what's
retenus
called
et
a
shortlisted
candidates
le
will meet
processus de
and
sélection.
bilingual
begin.
dual mono
Yes,
laserdisc,
you are amongst
French on one
the
channel and
people
English on the
of
other.
L'examen personnel des organismes des
and
Nations
the
Unies et les
major
tâches
tasks
principales
that we're
qu'elles
trying to
entreprennent.
carry out.
So just to finish this up, we can take the WAV file. And here we can hear just the WAV file
And
itself
the
playing.
Et les
major
tâches
tasks
principales
that we're
qu'elles
trying
entreprennent.
to carry out.
Perfect. Okay, so just to wrap this up a little bit, I just want to show you a couple of other things quickly. Let's build a new project, take an NTSC project. We'll call it Test 4. So one of the important things is, although I've shown you stacking and you've seen that the system can deal with multiple sources, the sources that it's dealing with, the only rule in the DAG is that the video format has to be the same. You can't mix NTSC and PAL, for example, but you can have as many NTSC sources as you like. So here I could, for example, load an NTSC source, and we'll go for something a little bit simpler. It's my test data, TBC, LDF, NTSC, CAV. We'll take Dragon's Lair as one example. Okay, put that out there for a second. Let's give this a name so we can keep track of what's going on. Dragon. Okay, let's add another source, add a node source, LD NTSC source. We can then pick a different disk. Let's take Firefox, for example. Okay. So now we've got two completely different sources. What we can do is we can dropout correct, two of them, source, dropout correct. Okay. And we can take those and we can sync them to different FFmpeg files. And again, just make these H.264 browse. They're out. This one is, we'll call it out one. Let's include the audio. Okay. This one, again, same thing, configure it. I'll call this out 2, include the audio. No, let's just switch this to the correct format. Out 2 MPEG 4 audio, yes. Okay, so this basically will now ingest two different sources and make two different syncs in the same project. It doesn't really matter. So when you trigger these, you can trigger them both. It doesn't matter that there are two individual DAG chains in here at all. The system will work perfectly well. So if you have a lot of related things or you want to do like one big project, you can put it all into the same project and it will produce the different triggers for you automatically, or the different output syncs. So you should be able to see an out 1 and out 2 in here. Here's our Dragon's Lair. And there is Firefox. So one of the things that we haven't looked at yet is the actual project itself. So here you can see our project. It contains two sources, two transforms and two syncs. So when the DAG executes, it will ingest the two different files and it will output two different MPEG-4 files. So once you've got this GUI project, the GUI itself is just a thin Qt6 application, a very thin layer that sits over Orc core. And Orc core is the processing library that actually does all the real DAG processing and does all the clever stuff underneath. So what this means is you can, for a start, you can actually look at the project file. And you'll see that project file is a YAML file. It's human readable. You don't need to use the GUI to create it at all. You could create it using an agentic AI if you wanted to. It's got a project name. Then it's got the DAG definition. The DAG definition is basically the nodes and their parameters. And then the edges of those nodes, so how they're connected together. So in this project here, where you can see we've got two sources being read, dropout correction going on, and two syncs going out. Instead of running this in the GUI, if you wanted to script something or you had a whole bunch of things that you want to process in a script, you don't even need to use the GUI. You can bring up the CLI, you can talk orc CLI, tell it to process, give it the name of the YAML file you want to process, and run. And there you can see it doing exactly the same trick. So it's basically taking the two source files and producing the two H.264 files. If you really, really, really want to see the processing going on, then you can bring up the log level. You can set that to debug, and you can even log to a file if you want to as well. And then you can see the full process. So that's it for the very fast introduction, really, to quite a complicated orchestrator. Obviously, this is brand new software, so beta is probably a strong word for it. Expect to see some bugs in it. There's been a lot of code that's been ported over from the original ld-decode toolchain, which may or may not function correctly, but it should be pretty much all in place. It's ready to go. Please feel free to try it out. If you do find any errors, or you have any ideas, or you have suggestions for it, feel free to go on the Discord or open issues with as much information as possible, please, so that we can look at the code and fix anything that's a problem.